Our system was built with the purpose of automatically adjusting the volume of a car stereo system. The goal of the system is to increase volume of car speakers in accordance to any increase in road noise, and decrease volume whenever a conversation in the cabin is detected. Aside from our intended purpose, the system could also be implemented in modern forms of transportation, including cars, buses, and planes, home portable and sound systems, and background noise canceling and reduction technology, including phones, headphones, and gaming mics. The hardware that makes up our system contains a model car made from high-density fiberboard, 3 speakers to create our external inputs being measured by the system, 3 microphones, and a strain gauge that the sensors use, as well as circuitry, DAC, and 2 power supplies that allow our system to function as intended.
Our purpose for implementing the strain gauge is to use it as a way to initialize our system. It serves as a way to mimic the driver sitting in the driver's seat, which would turn on the car stereo and start playing music.
The 3 microphones in our system act as our main sensors, collecting the data that is used to decide how the system responds to the given inputs. One is located outside the system to catch exterior road noise, while 2 are located inside. The one in the front of the car catches conversation and music, while the one in the back catches just the music. When inputted in LabVIEW, one is subtracted from the other so that only the conversation is recorded.
Our VI begins with the initialization or connection to the DAC, located outside of the while loop. Within the while loop, we have our default frequency setup, located in the bottom far right. This would mimic and indicate the default volume when turned on. Also noted in the loop is the HIL read used to read the voltage difference in the Wheatstone bridge. When the difference exceeds the compared value, it would turn on the Boolean operation shown as true in this case. Within this operation, the 3 microphones are connected to 3 HIL reads, each one named based on the channel it's connected to. Mic number 3, shown as connected to channel 3, shows the basic setup for how the signal is processed. It is sent to amplitude and measurements express VI, where the data is separated into negative and positive peaks, and mean DC. There, the positive and negative peaks are subtracted from the mean DC so the amplitude can be extracted. Since we have the positive and negative values to work with, the negative values need to convert to positive through the absolute function. Afterwards, both are organized into an array where the mean is outputted. When the mean exceeds the compared value, another Boolean operation is used to determine whether to add or subtract the default frequency. As for mic number 2 and mic number 1, both follow the same pattern as mic number 3, with the slight difference in the fact that both are subtracted from each other before being preceded. This is due to the fact that mic number 2 contains both conversation and music, while mic number 1 contains just music. Being subtracted means we can extract only the conversation signals where it can be then processed.
As mentioned before, the system turns on when the strain gauge is deformed and results in the waveform chart outputting a value greater than 0.
Hello, 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 hello.
Figure out what's on our heads. Let's talk about that.
First, normal sound.
Good mythical morning. Very happy to have special guest Maya Bialik with us today. Not only does he have a YouTube channel, he's also Amy the neuroscientist.